This is the screencast for section 5.4, example 2. We're going to use the fundamental theorem of calculus again, but now we're going to involve the chain rule. You didn't think it was going to stay that easy as example 1, did you? Alright, so we're still going to find the derivative of an antiderivative, which means we are opening ourselves up to using the chain rule, or the fundamental theorem of calculus. But now, if you notice, the upper limit of integration is not just x, it's x squared. So how does that come into play? Well, we're going to do it the long way first to show you how this works, and then teach the fundamental theorem of calculus way, the shortcut that gets around the whole long way. So the directions say find dy dx. Well, y is an antiderivative, so if we find dy dx, that's going to be the derivative of the antiderivative from 1 to x squared of the cosine of t dt. Well, I know that the antiderivative of cosine of t is sine of t, so I'll say we're still going to take the derivative eventually of, I took the antiderivative and that is sine of t, but we're going to evaluate that from 1 to x squared, which means I'm looking for the sine of x squared minus the sine of 1. Okay. So I'm taking the derivative of each of those. The derivative of sine squared is going to be the derivative of sine of x squared is cosine of x squared, but then chain rule times 2x. Then minus the derivative of the sine of 1, which doesn't matter what that is, the derivative of a constant is 0. So the answer here would be the cosine of x squared. As you may have predicted, we plugged the upper limit of integration into the variable in the integrand, and then times 2x. 2x should look familiar. It's the derivative of the upper limit of integration. Therefore, the fundamental theorem of calculus way would be, of course, stating by the fundamental theorem of calculus, dy dx is going to equal, so the cosine of x squared, I plugged in the upper limit of integration into the integrand, the input variable in the integrand, so x squared went into t, and then I have to multiply by the derivative of the upper limit of integration, 2x, and then I'm done. That's it. I could simplify, of course, and really you were doing that in example 1 too, or 1 as well, but the upper limit was just x, so the derivative of x was 1 and it didn't change, much like you'd been doing the chain rule all along before you actually realized you were using the chain rule, because the derivative of x is just 1. Then now try problem number 9. Says find dy dx if y equals an integral. So that means I get to use the fundamental theorem of calculus. So dy dx equals, now if I'm taking the derivative of an antiderivative, I have to state by ftc, so I can use the fundamental theorem of calculus and do this the short way. So first I'm going to say, wow, this is e to the, not t, but x squared squared. So not e to the t squared, but e to the x squared squared. Now I have to multiply by the derivative of the upper limit, so that would be 2x. And I could write that out as 2x, that would be e to the x squared squared, would be x squared times x squared, so x to the 4th. So 2x e to the x to the 4th.